So, hello, good afternoon, everyone, and welcome to the afternoon session of the APCTP IESCS SNBS workshop on computational methods for emergent quantum matter. So, in the afternoon session, we will begin by a talk with Professor Prasanjit Samal. So, Professor Prasanjit Samal obtained his PhD from IIT Kanpur in 2007. And then after a 2-year postdoc stint at the University of Minnesota, he joined NICER Bhubaneswar, where he leads the group on density functional theory and quantum simulations. And he's a professor there, and their group works on the interplay between structural, electronic, and magnetic properties of functional materials using computational methods. And today he's going to teach us about density functional theory. He will talk about its status, achievements, and challenges. Thank you.
Thank you to the organizers and particularly Manoranjan for giving me this opportunity to come and discuss about what we are doing. So there has been a lot of progress in this exchange correlation functionals, but it has not been explored by the application side or by the experimental. So that is something which is lacking. So I'll be talking on this one. So I'll be talking on this development of these functionals. So as Professor Dasgupta said, probably I will share some lecture notes. So some of the functionals that you can take as a home assignment, and you can come up with functionals. Okay. So what we are working on is basically it's already introduced. So we are working on this density functional theory. We are working on this conceptual things and these basic foundations and the advances of this density functional theory. So what we do the testing, benchmarking of these things, and then we give it to others. So they have to use it in various ways. Okay. So he's the guy, is my student. So he will be on day after tomorrow in your hands-on day. So he'll be helping you to use one or two of the functionals developed by us. Okay. So that is the thing. So whatever we have done, so as Professor Harpala has already discussed, it's all around solving the Schrödinger equation and how it is difficult to solve this one when you have more than one particle thing. And he has told several things. So I don't need to tell it again. I don't need to repeat it all these things again. So this is the physical thing. So you have to look at it. So this is basically how these electrons they try to repel one another. You have this Hartree thing. Then through this power exclusion principle, you have this kind of thing. Okay, so you have charge, you have spin. So there are charge-charge interaction due to and this spin-spin thing. Okay, these are the three possibilities. Okay, you have this one. Okay, so these three, looking at these three possibilities, the effective potential, which will be the electron will be subjected to, from that Professor Samal already discussed. Okay. Okay. So this is the Nobel Prize that is shared by this Waterphone and this John Koppel. So he has not got this Nobel Prize in physics. Here Professor Samal said several things about Slater. It's a Slater only for him. He could not get a Nobel Prize in physics. Okay. He wants to dominate this MIT thing. Okay. So that is not the one thing I think like about Slater. Rest of the things I like. So this is the Kohn-Sham picture. Okay. If you look at it, this is the interaction, the exact picture, and this is the Kohn-Sham picture, and this is the functional. Okay, the energy functional. Similarly, you can have other physical properties. Okay, so if you have to do force field calculation, you have to do fast principle molecular dynamics. There are classical MD simulations are there. So these are the things. Okay. Okay. So this is how you write down the Kohn-Sham contents of this Kohn-Sham thing. You have the kinetic energy which is there. You have the Hartree thing. This is the exchange integral which Sarah has shown. Then you have used the orbitals. So what kind of orbitals you use, depending upon that, you get this thing. So you can from here you can do two ways. There are two ways. You can go either in the wave functional way or you can go in the density. Okay. So this is from here you can bifurcate. Okay. So the purple and John purple and this water cone thing, this is basically the from where they have gone in the density direction, and other one is the away from something. Okay. So the only quantity which was unknown is basically this quantity, the exchange coefficient. And there has been a lot of developments for the last 4 decades about this exchange and correlation. Okay, and this is the Jacob's ladder, which is proposed by John Porteau. He basically copyrighted this exchange code. More or less, John Porteau and there is another guy from Cambridge, Axel Beatty. So they have this copyrighted all these functions. Okay, so that is the thing. So they have been developing this thing, and in recent times, so there are few people who are now working on this functional development, and from here we are working on this functional development. We don't know how we are doing better or not. That needs to be explored by all of you if you are interested in this electronic structure. Okay, so that is the main motivation why I will be talking about this one. I will be sharing the notes as I said, so that you can also derive the functionals on yourself. Okay, so that is the thing. So when you develop functionals, so it depends on the ingredients on which the functionals depend. If it depends only on density, that is called the local density approximation. If it depends upon this gradient of density, that is the generalized gradient approximation. And there could be, if you coin the dependence on this orbital, if you coin the orbital dependence, then it will give you better result, that is meta-GGA. Okay, then you come up with hybrid functionals, as Professor Abdullah said, that it will also have this density picture and this wave function picture can be mixed together. Okay, so if they are compatible with it, they can be mixed. So that you cannot mix it arbitrarily. Okay, so that is the thing. And then this when you do this cone something, so people generally think that you cannot do for strongly correlated systems or strictly correlated systems, but that is not true. Okay, it depends upon how you approximate your functional. How, to what extent your many body effects are there inside your exchange correlation, that allows you whether you can use it for this very strongly interacting electrons or strongly interacting systems. Okay, what functionals we have developed that is giving results comparable with the GW calculation, GW BSC calculation for all these things. Okay, so this is something I used to emphasize, that it is not the defect of DFT. It is our demerits that we are not able to develop good functionals. Okay, so it's not a defect of DFT as a whole. The theory itself, it has everything that if you, depending on our capability, if you can develop good functionals, and then you can have this. So when you define, when you construct functionals, so how you construct functionals, so these are the ingredients, as I said. These are the things on which this functional development basically takes place. Okay, so these are the things. So these are the quantities. How it depends, how it differs for. This is for homogeneous electron gas. There is something. This when you have density, either it will be slowly varying or it will be rapidly oscillating density. So depending on that, you have this functional thing. Okay. So the strategy behind to how you approximate the functional, there are two categories of functional. One is empirical, one other one is non-empirical. Okay. Then in the empirical, you have fitting parameters, and you introduce several fitting parameters to make the functional better. So these are the functionals which are like this empirical functionals, and here these are the functionals. These are non-empirical functionals where you have to use the exact quantum mechanical constants to derive this to construct this functional. So these are like this non-empirical thing, and there are also semi-empirical functionals which depends on semi-local quantities. So this is the recent functional, very recent functional. So it goes back to this 2020, 2021, 2022, these functionals. Okay, and so I was telling something about the scan functional. So the scan functional, so it's basically there are several constraints which you have to satisfy with that is like positivity, negativity, slowly varying, rapidly varying, and you have these bounds. All these constraints are there. Okay, and these that functional is the scan functional. So looking at the system, depending on your experience, this body was developing this functional for the last almost 3-4 decades. So from there, he had hands on very good hand on this functional. So he had this 17 constant, and later there has been these constants have been removed in some constant that is called the regularized scan functional. Again, that constants are again re-put back in the scan the device scan functional. That is means there are 3 functionals in that group: scan, R-scan, R2-scan. And the functionals we are doing this RMGSE and other things, which are also very good functionals, but it needs to be explored. So it's just started. Okay. So as I said, on which these functionals depend: the spin up density, spin down density, and the gradient of spin up, spin down. And this goes to the if you have this kinetic energy expansion in terms of this density, that part goes back. And this is also, if you want to bring the exact picture of the system, and you can think of that as if the Kohn-Sham orbitals has some meaning in it. Then it has been found that this not only the highest occupied Kohn-Sham orbital, the low-lying states has some thing to do with this functional. So this is like you have this kinetic energy density, and this is how this functional depend. Okay. So this is all about this thing. And then while developing the functionals, so it is not that you have to start from scratch every day. Okay. Starting from some of these functionals, you can further develop on that functional. So that can be done. There is some function which is called enhancement, this enhancement factor. And this functional enhancement factor tells you how good is your next functional from the prior functional. Okay, so that's how you keep on changing this enhancement factor. Okay, so this one, okay, it can be there for exchange, it can be there for, like here you have for exchange, and here you have for correlation. Okay, now that is the thing. So what is happening? So this is a dimensionless quantity, this enhancement factor. So what will happen that when you target to construct a new functional, okay. So depending upon what kind of things systems you want to investigate upon, so these quantities need to be approximated for exchange. If you want to do spin polarized calculation, you have to do something, the spin scaling like this, and you have to do it for spin polarized calculation. Okay. There is called something called the scaling of this functions. Okay. Okay, so this is for LDA. How this LDA is constructed, the starting functional, you take this plane waves and you evaluate this exchange integral, and then you get this LDA functional to be this 3k open 4 pi. What you are was showing that 3k open 4 pi minus 3k open 4 pi. If you use that homogeneous this plane waves here, and then you do that is the LDA function. Okay. Now, with this LDA thing, then you take this correlated approach, then you do some fitting thing, and then you come up with the correlation function. Okay, so that is there. LDA thing is there. You have to. Okay, so what is the problem with this LDA? So it's these are like you have this this finite thing, this correlation and other thing. So it is satisfied. So there are several problems like. You have this when you have this low line and low line density and this high density limit and low density limit. So problems in the LDA comes because of that thing. So there are several problems with LDA that sir has already told you. So that should be further development on this functional. That is for the next functional is this generalized gradient approach. Okay. So the next round of this functional is this. So this is the atomization energy, which is a problem in LDA. This LDA means this if you do this higher version of this local spin density approach, this is the problem. Okay, and you have like when you do the solid calculations for extended systems, if you do so this is like these are like finite size systems, and these are like extended systems. So the lattice constant or other things, this LDA still shows this problem. Okay, so that drives us to for this next level of accuracy in the exchange correlation function, that is the generalized gradient approximation. And when this is a non-empirical functional, so when you do this generalized gradient approximation, so there is a dimensional quantity. I said the enhancement factor. That enhancement factor needs to be written in terms of this quantity. So this is called reduced density, reduced gradient density. Using this one, this is the enhancement factor for the extent that is written. It will be written like this using this thing. Okay. So, that is the first step towards the construction of this generalized gradient approximation. So the GGA functional looks like this one. Okay. So what is happening? So the GGA, the functional, it should also recover the NDA property in certain limit. Okay. So this the linear response and the bounds, this exchange correlation analysis can not be, it won't be like it. This is like you can achieve any value. Okay. There is a bound on this exchange correlation analysis that is called something called the Lie-Oxford bound. Okay. That need to be satisfied. Okay. So that is something. Looking at that one, the enhancement factor that will be constructed for this one. And this the construction of this one, I'll send the notes to the conference people. Then you can work on this one. You can get this enhancement factor. This is the starting enhancement factor. If you can understand this one, then you can come up with other enhancement factor. But but it cannot be arbitrarily. You cannot do that. So you have to use certain constraints and other things. So impose conditions to come up with this enhancement factor. So this is the GGA functional. Okay. So this is for the exchange part. Similarly, for the correlation part, you have this. The reduced gradient or density gradient is different, and then you have this like the spin polarization factor like this. Okay. For the correlation part. Okay. So you have to, so the correlation functional, it will be look like this. So this correlation functional, so it goes to Purdue in 1992. So this is the correlation functional in the second round of the exchange correlation Jacobs method. Okay. So what is happening? I said that this is a slowly varying limit and the rapidly this high density limit. In the slow density limit, so there is called so when you do this expansion, you have second order gradient expansion, fourth order gradient expansion, and all these things are there. Okay. So you do the plane wave analysis. So it's when you do the local density approximation, there you have used the plane wave. Similarly, here you have this second order density gradient expansion, and then you use the linear response criteria and you come up with these functionals. This is GGA functional, and the quantities it will be like this. Okay. So that part is for the slowly varying limit, and this is the rapidly varying thing. And in the rapidly varying thing, this is the thing. So this is mathematically a bit tricky, but if you do this thing, once you do this gradient expansion, so you have to start with the plane wave and then you do the gradient expansion. It is not that difficult. So you have to understand how so in density functional theory, you have to look at the system density, means the density of states or that thing. So how this density profile behaves, and then looking at that thing, so it can need to be incorporated through the functionals. That is what your Weinberg-Kohn theorem is saying. So instead of doing everything in terms of the wave function, as we are now doing it in terms of density, so everything starts from the density itself. Okay. So similarly, here also you have this PB thing. This is the enhancement factor. This is the constant that is you will get this constant for the enhancement factor. So this is basically the advanced level of PB functional that is useful for the solids. Okay. So there is a two PB functional, GGA functional, and there is another functional, GG functional for solids. Okay, so this is called your PB. So PB is basically called the generalized gradient approximation. That is the first thing, but there are, however, other GGA functionals are also there. So these functionals, they can either work well for the molecules or they can also work well for the solids. But there are certain functionals which will work well both for molecules and solids, and those functionals are better functions. And these are the functionals. This is called the meta GGA functionals. So which use this orbital picture in it. So this is like you have this the PP and PB's this PP functional and PP functional for solids. So this one is solid thing. And if you look at this one, okay, if you look at this PP functional, this is better for this molecules, and this one is better for your solids. Okay. So this is the thing. So what you have observed that this PB functional is performs well for this solids for slowly varying density, but these are not good for molecules. However, PB performs good for solids, not good for, which is not better for solids. Okay, but this is not bad, but it is moderate for this molecules. So the question is, what is the problem? Where the problem lies? Okay. Why one is better and other one is not better? That is the thing. So it is because that the linear response criteria which is used. So this linear response means you have this OPM method, I was telling. So you have this response function. Okay. So here also, whenever the density is changing, okay, the functional itself will keep on changing with the density. Okay, so you have to see what is the response of the system. Okay, with the response of the functional with the system. System means there is a change in your density. Okay. So you have to look at that and you have to construct your. So this linear response you must have done in your this manual physics. Okay, and this linear response theory. So that is the. So if you look at this one, there is another functional which is taking into account whatever problems that is there with this PB and PB sum, that is the PB, which was well both for molecules and so in this category, these three functionals are quite famous. This GGA function, either this is PB or PB int or PB sum. Okay. So what we have learned that the GGA functional, as such, it is not always good for some finite size systems or extended systems. So we need to go beyond those functionals, which will be better simultaneously good for all those systems, this molecular system as well as the solids. Okay, and that is basically the next level, next range of the functional. These are the meta generalized gradient application. This is called meta GGA function. Okay. So what is there in meta GGA functionals? So the requirement is that it should work well for solids and molecules. And so in the morning session, you lot of things has been discussed about the self interaction. Okay, the self interaction program need to be taken care while you are constructing the functionals. Okay, so that part that is a problem in GGA thing. Okay, GGA correlation functional, it is not a self interaction free correlation function. So if you make that to self interaction free, then that way you have to do. So how will you do that thing? So you have to do it for each individual electron. So when you are talking about these electrons, that means the orbital picture should be there, and that's how the functional will now depend on the orbital. And in the whole density functional, what is the quantity that depends on the orbital directly? The Coulomb kinetic energy. Okay, so that is how this Coulomb kinetic energy density will somehow come into picture of this function. So way back in 2004, this Portimer and the Swisseria, they figured out that thing, and then this is another person was there, Gian Mintao, he passed out. So he has done a lot of work with John Porty. So that is the thing. So how it is the self interaction need to be included. If the self interaction will be included, then the correlation for one electron will be 0. So that is the thing, and that is how this meta GGA functionals are constructed. Okay, and as I said, this is the kinetic energy density that will go into the picture, and the functional will depend on the various ingredients, and these are the ingredients. And this is the alpha is the ingredient which depends upon, you can see both Z and alpha, which depends upon this Coulomb, this kinetic energy density. Either it will be Thomas-Cohn kinetic energy density or it will be Cohn-Sham kinetic energy.
Then why did you say EC should be 0 if the reflection is correct?
So for one electron.
EC would be 0.
Yes.
Or EC plus that would be 0.
No, the whole correlation thing for one electron will be 0.
Your exchange is cancelling.
Yes, yes. So that thing will be 0 for one electron. That is the main thing. Plus the target is that the functional should work better for both for molecules and solids. So that is how the idea for which prompted to the construction of this meta-J function. And these are the ingredients you can see which depend on this kinetic energy density. Okay, so that is the thing. So this is how this density, how these quantities are changing for various things, which is given here. So either you have covalent bonding, you have non-metallic state, or you have non-covalent state. So these are the ingredients on which the meta-J functional is constructed. And this is how earlier it was up to here for the GGA thing, up to here. Okay. Now you have this quantity, these two quantities for meta-J functional, both for exchange and correlation. Accordingly, your enhancement factor that this here will keep on changing.
So one more question. When you do meta GGA, you said it's important to have phi I in it. So why do they do kinetic energy? Why not phi I mod square directly? Is it because kinetic energy also has gradient of this?
Kinetic, no. So this kinetic energy, on this conjointness of this functionals. Okay, what it tells that the way you are having this exchange correlation functional, the same gradient expansion, second order, fourth order gradient expansion can be done for the kinetic energy.
So whatever the ingredients are there, you will
The same can be done for this one. So this Ludena and others, they have this also this Marx had this kinetic energy functional. But Ludena has shown, Ludena and Dressler, they have shown that the kinetic energy also you have second order, fourth order gradient expansion, and there is a functional form is also there. Okay, and also during this minimization process, when we are minimizing this kinetic energy in the Cohn-Sham. So that would be better if the orbital thing will be included through the kinetic. So now, say we have constructed the meta-J functional. So these are the results you can see. Okay, these are some test sets for which you have results for the LSD, local density, GGA, and this is the GGA hybrid. Okay, and this is the another GGA functional by Podripur, Jupan, Lahar. So before this PV, that result, and this is the TPSS, that is the 2004 function. Okay, and in all the cases, if you look at this meta-J functional is doing far better, quite better compared to the GGA functional. Okay, but still all is not well. We'll come to that. Okay, and this is like the problem is that so. What is happening? There are some cases where the meta-J functionals are not better compared to the GGA functional. Like you have the phase stability. Okay, if you have the structural phase transition, okay, so there this functional is not doing better. This meta-J. Okay, so that is another thing. So what is happening while the construction of this meta-J functional? So there are several things that is done. Suppose you have three things you are doing together. So what it has been observed that if you have, say you have a first process, second process, third process. Now in meta-J functional, if you do the second process first and first process second, then there is a change in the this results of this function. Okay, that is called order of limit problem. Okay. That order of limit problem that need to be fixed if your meta-J will do well. Okay, so that's something we figured out. This one it was not there in the scanning functional, and we figured out that there is a problem where why this meta-J functional fails. Okay, then we fix this order of limit problem. So there are two things. If you do this one first, alpha going to 0, then P tends to 0. Then this quantity is 1. Figure out. And if you do the other end, this quantity you are getting 0. So what is happening while doing a functional construction? You have done several approximation or this whatever process you have carried out. So many this gradient expansion thing. Okay. So there, what is happening? They are inconsistent in some way when you are dropping some terms or you are approximating something. And that need to be taken care, which were not taken care of while they proposed the meta-GJ function. And that we fixed this problem. Okay. And then we figured out after fixing this thing, okay, we are getting the phase stability to be better phase stability we are getting. Okay. So we have this this TM and this functional. So this is level. So we have found out a new functional for structural phase tensor. This REG.
So your F alpha P function. It has the same limit whether you go alpha equals 0, P equals 0.
Yes. So it is
Order
not
doesn't matter.
It doesn't matter.
So what is the function?
That is that. So we have this density matrix X function. Then this is the function.
So the function. What is your F alpha P?
That I have not written. So that function. So this is there here in this paper.
But you have fixed the problem of this order
Order of limit problem. Okay. So now what is happening that we have this meta-GJ functionals. Then there are several meta-GJ functionals. Then it has been shown that all the constants are not satisfied by the meta-GJ function. So what you did? So he collected all these constants and then he summed up this constant to 17 constants. Some constants to be satisfied for the exchange, some will be satisfied for the correlation, and some will be satisfied for both exchange and correlation. So there are 17 constants. So using those 17 constants, so he has given this scan function. Okay. So it's basically your enforcement of the constants on the exchange, this functional construction. So what is happening? He has observed that this enhancement factor which we have obtained for scan functional. Okay, so it has been observed that this the scan functional also this we have checked that it is free from order of limit and this is the strongly bound thing from the GG and other. Okay, so this order of limit problem he has not investigated, but we have figured out because of the satisfaction of so many constants, the order of limit problem has gone. But in our case, without looking at those constants, we figured out that in the while you while you develop your enhancement factor, there you are doing several steps. You are omitting several things which are necessary. Okay, so it is not the constraints. If you impose that, your functional will become better. Okay, without imposition of this constant, if you take the physical picture into account, what is physically happening exactly, so that is the many-body effect. The more you include it in a proper way, better way, then the functional will be better. So this is something. So this scan functional, it has not been constructed. So the scan functional is basically imposition of this constant. Then they keep on changing the enhancement factor. Okay, but the scan functional also, there are problems with the scan functional also. If you have you are saying all the constants you have imposed, it should work well for almost all the systems, but that is not happening. Okay, so that is the thing. So for this enhancement thing, so you have about the scan functional. Okay, so this is the parameter. Then what is happening? The sum of the constants has been relaxed. So what it has been saying that if you relax some of this condition, the scan function is working better for some system. Earlier, the pure scan function, it was not happening, but if you remove the constant, it is working. So that means there is some loophole in the construction of the functional, which you are not going, but from outside you are imposing the constants on the enhancement factor. So because of that, the systems you might have investigated for which it is giving good. But it is not. So that is the R scan, the revised, the regular scan thing. So you relax some of the concepts. Then again, what is happening? There is another functional. Okay. So that is like again, if they impose the constant above this one, that is called the R2 scan. Okay. So this is the picture first scan. This is the original scan. This is the relaxing the constant. Again, putting the constant. Okay. So in some cases it is giving good thing. In some cases this will be good, and in some cases this. But there is not a consistent thing about the scan function. So that
is the difference between R scan and R2 scan.
so what is happening here is the 17 constants are there. Here what they have done, some constant they have completely omitted, and they have seen this is working well better than this. Now this one, these are the enhancement factor. With that enhancement factor, they again put some extra constant, that is this, and this is giving better result for some. But there is not a consistent thing on these three because the constants being imposed from outside without going into the actual how the enhancement factor should be. That is okay. So basically, what Purdue proposed, that is basically from experience. He was doing everything, okay, on this. So that urges that we should be doing something, okay, that should give the good result for the expression. So this is the functional, okay. So it's like the MGTSC functional, where we try to come up with a functional which will be either at par with the scan, okay, or it would be better. And this also, we are seeing very recently, this is also not good for in some cases, and this is also so. This is like in the beginning phase of this function. Okay, so this is a new function. So it has not been explored by many. So because they are always using the scan or R scan, but this is there in this vast thing. So it will come out in the next few of the class. Okay, so once it will be there, so we'll be working on this function. So how it will be, it will take care of the problems of scan, R scan, and R2 scan. Okay, and this while you are doing this functional construction, so this is the density. You have to start with some density, and we know most cases. So what is the density which is more known to us? The only problem we have solved is exactly what? Hydrogen. Okay, so whenever there is more than one electron, even the helium thing, we are solving variously. Okay. So what we have done, so the Purdue and others, they have started with the hydrogen thing, and there is something in the DAT, there is something called the nuclear cost points. Okay. So what we have done, that we started with the costless hydrogen density, and then we try to come up with this first. So this is there, this is reported in the papers. So starting from the costless hydrogen density, we propose this metal. And that functional, so this is the costless hydrogen density, and then we come up with the this is the exchange correlation hole. Okay, so when this exchange hole correlation hole means, you know, because of the charge and spin, the electron around its surrounding is in the surrounding doesn't allow another electron. Either it could be due to the charge or it could be due to the spin. And the space which is divided by the rest of the electrons, that is basically the kind of a hole kind of, that is a vacuum around the electron. If it is due to charge or if it is due to spin, so accordingly you call it exchange correlation hole. Okay. So we started with this one, then we come up with the exchange correlation hole. Okay, exchange correlation charge density. The integral, that is the exchange integral we have written. The exchange integral can be written in terms of the exchange. In the morning you have seen that. Similarly for the correlation. So that is how we come up with this functional. And then, so this is the process of this functional construction. Okay. And our enhancement factor looks like this, something like this. Okay. Now, if you look at here, okay, you can see the results that we are getting here is sometimes it is quite better than the this thing. This is the scan. Okay, so this is there are results here, experimental thing which I have not shown, but this one works well for almost all. Then, so this is the thing how this you have this comparison. Okay, the relative percentage of error we have figured out.
What is the sets? NC20, BM20.
So these are like there are some tests. So why this Don Fuller in Minnesota, these chemist people, they always go for the testing and benchmark. If there is a lot of development in this many thing that is mostly due to the chemistry. Okay, so they give a lot of calculation. Okay, so looking at that data, you do this, and what we have figured out, you look at here, see the relative percentage of error. So MCGS is given this better one on the this. So this is again with some the comparison. Okay, so this is with the R2 scan and all these things. Okay, so the before this MGGSE, this is the pro. Okay, so these are the results you have for the strongly bound, weakly bound thing for all these things. Okay. So these are the results where you have this dispersion corrected functionals or Van der Waals density functions. When there are systems where the dispersive force is important, okay, there you can do this dispersion correction. And also for strongly correlated system, you also heard about the Hubbard. Okay. Now, earlier the Hubbard was with only the GGA. Now you see, we have done it for the meta GGA also. And also that includes the Van der Waals forces. Okay. And we are working on this one. So actually we are working on this one. Then for the last 1 year and so it has been stopped. So again, my students are there. I hope they will take this further. Okay. This is very interesting. All your course you must have seen about this GGA plus U. This you may not have seen this. You have meta GGA, you have Van der Waals force, and you have also the Hubbard. So it's not that it's not working well for strongly correlated system. Okay, the next suit of this, whatever DF course will be coming, this will be coming with this, whatever we are doing. Okay. So it will work well for this strongly correlated system. Which now people are thinking, no, DMP is not doable for strongly correlated. That is the wrong perception.
Prasanjit, the audience here, can you, if somebody is interested, can you make your course available, or are they going to be coming out in fast or something?
This will come out in fast.
When?
I don't know. That next to be there. So this is a commercial package. So you must be knowing. So they have given us the source code. We use that one. We cannot share that one direct. We don't have our own.
So if some of the participants are interested, what can they do?
They
They are
can do
interested in
it.
applying your
They can directly work with us. We can do that. Also, they have to understand this development also, or which you can share or way we derive it. That is need to be understood. If that is done, they can also implement it on their own fast. They have to write a subroutine for the exchange correlation and call it in the main program and do that. Okay, so this is something you have heard about this transition method also. This is the problem for earlier functionals, but this is not for the meta functional we have developed. This RJ and MGGS. So this is reported in this paper.
So when you show this graph, what is it showing? I mean, I don't. Could you just explain a few things?
So this is like you have this comparison between this. So it's like this zinc blende structure and this what is that? This from
Number or something.
rectangle marker something. So this is for that.
No, so what are you showing in the graph?
So this is like how means
The difference in the energy?
energy that is going in the positive or negative.
What is it supposed to be?
This is the like there are this experimental thing that is also kind of this kind of thing also.
Where is your functional in this?
No, this is for our thing, but there are other pictures which is having the experimental. That,
Where is your functional in there? You're showing
here,
PDE.
this, no. Here you have what is this? We have shown how you will do a semi-local function, which you have not done with their Hubbard U and Van der Waals.
You added that to this PBE, GS.
Yes, yes.
Okay.
And then, so you are there. So if you look at this one, this thing, you will see this one is that our function is here. It's there. This is our functional, what we have shown, that in scan and other thing, whatever you are doing, they are getting this result with this, what is this, with, so this should be good for this part. This is the line, this is the zero line. Okay. And you can see the variation of our thing. This is without doing in Hubbard U on Van der Waals.
Okay.
In our functional, we are, it's like, it's better for strong correlation and for dispersion.
You're saying this should be close to the dot dashed line?
This no, so this is like the zero line. There should be no change kind of.
But then how are you doing better? You're not getting zero.
This one.
Ah.
So we have not done any Hubbard U and this Van der Waals. If you look at here, this is only pure functional. There is nothing added here. So what you have seen, so it's like scan, you can check here scan.
Okay.
It is going beyond. That is the thing.
So you don't have to do any trickery.
No. Now if it, so what is, that's what I said, that if you do Hubbard U and then this one, then we'll be getting even far better.
So let me understand your philosophy of developing these functions.
Yes.
So there's this, as you say, LDA said that you satisfy the whole condition, normalization. Then people put different conditions, exact conditions. What you have come up with is you don't put exact conditions blindly. You look at something, some mathematical things that are going wrong in doing so. If you do it consistently correctly, you get a consistent answer. Is that?
Yes. So what is happening while we started with the hyperfocus and everything, we are just looking at the normalization of the whole. We are not looking at anything else. Now, what is happening when they approximate the enhancement factor through various parameters, be it empirical or non-empirical things, then this is the problem arises.
Mathematical problem.
So that is the.
So it's really you have found out a real thing what is to be done. So if
We are thinking we have found out, but that need to be investigated.
so this FRP that you are developing,
Yes.
whatever, so it is quite easy to implement. I mean, if others can understand it, they can also use their own thing. They can model it, right? That is very nice.
So this is the thing we have. This is the various phases. This pyrite, marcasite, and this is, you can see the result. See, this is the thing. So this experimental thing, if you look at this one, so this is the error we have made.
It is getting the right sign. And then delta RA.
Sorry, RPA is so bad.
Which one?
RPA.
This one. This is no. This is a RPA.
with PB.
R2PB. This is not so pure RPA.
Okay.
So as I said, you have these fitting parameters and other things for correlation. This should be from some purely correlated thing. Then you have to compare. Then you fit and take those parameters, and then you come up with the enhancement factor for correlation.
But with RPA on top of the function or whatever.
This one here. But here, whatever we have done, this is some parameters should be taken from it. The function is already there. So you will do this, take this quantum orbital, you do RPA or you do GWPS, whatever you do. But your orbitals are not in a proper, whatever you are intending for, that orbital is not supposed to.
Very fair.
So this is the thing. So this is the metal insulator phase transition. So this is we are working on. Okay. There is something about this band offsets. So he was talking about this ionization potential, electron affinity, and other things. So there is something called the band offsets. You have this band offset. So here also we have figured out the meta-GJ functionals. So how they will do well for these band offsets. So this functional here, the RMCGSC function. Okay, this is the GWBSC. You do the GW thing with the hybrid function. And you can see this is blue lines. So this is how this functional is done. And this is, remember, this is without any constant and anything. There is you don't have to bother about anything. Just costless hydrogen density we have taken. Somehow we thought of something and do. So this is what happened in my PhD time also. So me and Sir, we are thinking about how to develop functional for excited state. So we are doing something. And all of us suddenly just tried, we did a K gap in this Fermi shift. Okay. Then we fixed that K gap, the radii using the cone sum. So that is how something worked out. What we noticed in for this one, so he never shared his thing. Like as I said, if you are interested, I will send you the notes. So what we have seen that he's doing, he has done everything with the hydrogen density, and then he was doing all this plane wave analysis and the G, gradient expansion, fourth order, second order, all this. Then we noticed that there is something called the cost condition that is not satisfied by the pure hydrogen density. So let us have a costless hydrogen density. Then we worked out and then we got this. So if you are really interested, so whatever you are doing, we are doing many thing or finance matter thing. So anyone can do this development. It is not difficult. So you have to think of what you are intending to do.
Tell me first one thing that slightly of more of a logistics thing. How much difficulty do you have in publishing this work initially?
This one.
All the work when you're doing functional, because again people kind of hold on to this our functional, nobody touches it.
So initially, when we are working on this density matrix expansion, our first paper it was 1.5 years. It got rejected. There are 2-3 papers. It never published. After being reviewed in the physical review, it was found 780 paper, and then we fed on something. But some portion of it later on we worked, and this is published in the. You know. The BRB I was showing.
Don't worry, I mean, for any development of the
No. So that is the thing. You know, what is happening in between for 6-7 years, everyone is thinking we are not doing anything. So that is the thing. So if you are working, someday it will pay. So that is the thing. So this is like the band offset. What we are getting good thing for our function. And you can see the results. Okay, so this is our function.
Band offset means that you're plotting the offset, how much it is off from the
All
exact.
from the place. And this is the results for this one, the GW.
One has to know that GWHSC is very, very difficult and
No,
one
it's
doesn't
very
know. They will be learning about GW tomorrow.
Yes, Manish will be there. I don't know, Manish is aware of this function. So his students are there, they will tell you.
what exactly is that function? Why it is?
This function.
No, the last one, why do you think this?
This is the quasi-particle thing. You have this quasi-particle excitation mixture, this TUV point thing. So they have started it, and the thing is that they are from Berkeley. So that is their
No, they wrote I have this function. Steam Coulomb, W is the steam Coulomb potential.
Coulomb potential. Yes.
Then they do first order perturbation theory. I think second order perturbation theory close up again.
Yes, yes.
This first order and second order actually it is completely wrong result. Because
I have no idea.
because depends on the amplitude you are taking.
Mhm.
Depending on that, if your perturbation is truncated, it can be completely off. If
Yes,
your
yes, perturbative theory is just like that only. It may not take you in the right direction. Traditionally, Directional thing is a better thing than the potential.
That's correct.
Either it will hit your global minimum or it will hit your local minimum. But perturbation, it can go off sometimes. Perturbation means something is completely perturbed.
If your starting momentum is not good, then you have a pen. Whatever you do, that's no, it is the perturbation you are thinking, which is not very sure that your instinct is not.
That's why the self-consistent things is better. But this is so enormously expensive. It is almost next to impossible doing that.
And it's always.
Okay. So these are the take-home messages for the meta-GGA functionals. So these functionals should be accurate for both. It should be more accurate for the GGA, and it should give you it should address properly the band gap problems and the dispersion and the band one thing, whatever I said. Okay. So that is the thing. So there are several things about this meta-GGA functional over this GGA. So next is hybrid function. Okay. So you have this picture you have seen already. You have n-1, n, and n+1. And then whenever you have these functionals, they should mimic properly this kind of thing. Okay. So that is the thing, and then this you have the self-interaction tree you have to do, and the fractional thing, the fractional charges also here. If you do it up, it could be a fractional. So this is the thing that helps you to construct the hybrid function. So there are three major categories of hybrid function. One is global hybrid, and another you have this range separated hybrid. Either then it's a range separated, it's a long range corrected hybrid or short range corrected hybrid. So three categories are there, the hybrid functions. And this is very nowadays has a lot of use in the hybrid. Okay, for this optical properties, and because it works well for this molecular thing, you have say charge transfer excited state or this spin field excited state. Through hybrids, you can do it better because this hybrid functions it has the asymptotic behavior is quite good.
Range separated. In range separated, not in the other one.
Yes. So this asymptotic correction means if your asymptotic is good for this function, it will give you good. Okay. And then you have this range separation. That is a range separation criteria for the hybrid function. Okay. So it varies from functional to functional.
So from where the ratio is
This ratio, you have this see, whenever you have these results for LDA and Hatrifat and other, from your systems also, you have seen to have from the density profile of various systems. This can be fixed.
I thought Becky parameter fitted it.
Now, Becky,
Funny.
Becky, you have this Becky parameter. Also, you look at that density profile of some of these systems, this D3 and other things. That is how that is, these things are coming.
But it's semi-empirical. It's
I
not.
mean, no.
depending on different materials.
So what is happening? You have like you have a whenever you do this one, you have a Hilbert. In the hill, so it's basically we are getting this wave function. So how we are getting good result? This is basically we are mimicking well the Hilbert space. Okay. So what is happening? You have a subspace of the Hilbert space. So the functionals that you are saying that if it is a you have a subspace where this function is working well, say D3. If you have a smaller thing, then it will automatically work well for that. So on this basis, I think you have this thing. So that is basically you don't have to bother that much for in all the systems, which are problematic systems. There you have to be very okay. So this is how you do this one. So here it's a density functional approximation. DFA is density functional approximation. You can use various functions. Okay. Okay, that sir was saying this morning. You have this exponential kind of thing. You have this error function for this range separation, and you do this write down this global range separator hybrid function. So this is how you your range separation. Once you do this mu, so this thing you have how the profile looks. So you have drawn this picture in the modules. This one and this one. You mix this one. So that is the. So it's a long range correction hybrid. So what we have done. So we have couple of functionals for these hybrids, which are even sometimes better than your B3. Okay. So this is already there in QK. So it will also come. So this. So here it's our these are the test sets for which you have our this. So you have this this hybrid functionals. You should work well for the solids extended systems. Okay. So this is done with this ADF package. Okay. So these are the things. So this is appeared in this the results appear. So it's like this long range corrected density functional approximation. Okay. So this is how the if you know the long range, short range, this is the breakup what how we have run. And this DFA, the density functional approximation, is the functional of hours we have used. So this is the thing is that once you understand well the functional construction, then you can do this tweaking and this tricky things. And this is how you do the this hybrid thing. That is basically depends on that is so these are the results. So we got this thing.
What are these band gaps?
These are the band gap. This
The total energy, MEV per atom.
MEV is
Is the
no, this is not right. This figure.
I think energy.
Was
0.5 silicon is it's not right there because 1.7, so 1.1. That is energies.
these are coincident. So these are the lattice constants and bond coincident. So this is how we have got. This is the function. SRH this function. Okay. So this is the dielectric function. So there is something whenever you have dielectric dependent hybrid function. So this is the dielectric thing. Okay. So this is the range separator for this, as I said, our functional. This is our MGGS. How we did the range separator, short range, and the long range part. Okay. So this is with our functional, we have done this hybrid functions. The functional, the meta is a functional, we have functional. So this is the recent one. There is this another important functional. This is the tau function. So we have done this short range hybrid functional for tau and also our function. And this is the result for dynamic multiple. So this is how it is in the past code. So day after tomorrow, so we should not will tell you about. Whenever the code will be talked, you can use this. So this there is another something called generalized Boltzmann approach. In generalized Boltzmann approach, you have this nonlinear thing, the Hartree-Fock. Okay. So it's also an effective particle kind of thing. Okay, so you solve like a cone sum. The way you solve the cone sum, the similar way you can do this generalized cone sum. Okay, here you can use this. After you add this one, this is how your exchange term will look like. So this we have done this GKS formulation in this past. That is there. So we have several things done in past like GKS.
Have you plotted the corresponding exchange correlation potential from there?
Yes, we have. So that is how we first do that. So when we do some function, that is the first thing we do.
No, so how do you calculate? Because now you have orbital dependence and all that. How do you calculate the potential?
Not all cases you can come.
Or you do basis calculation?
You can do basis. Yes.
Then you don't see the potential.
No.
You just imagine the energy.
Yes.
Fine.
But you can do that thing. OPM you can do by looking at what is that? One is this IoT connection that you have. You have the system to system IoT connection. Now we can do something from this energy functional to the energy functional through the potential. So this potential driven. So if you from that way, if you get the potential, it will be easier to do the calculation. You don't have to go to this, all these terms. So this is like I have finished.
Okay.
So these are the papers. Don't bother about this.
Thank you, Professor Samal, for the tutorial session.
I just have one.
So questions.
I mean, as one of the small organizations in Ranjan is, one of the purposes of this workshop is how our students here working can benefit. So one thing you're sending your notes if anybody wants it.
Yes.
Other thing is, if they want to run it, do you have a visitor program? Can somebody come with their course, sit at your place a month and a half? Most
They
students.
can come in the summer, 1 month.
So, but suppose it would be they want a short visit, 2 weeks, 3 weeks, 4 weeks. Yeah. So you haven't given your email address. How they write to you? No, so I really want to advertise this. There's a person who's doing this, and you want to implement certain work that you're doing. His programs have been put on VAST. Programs have been put on QCAM. So the person you can really go and visit, and they have a visitors program. Bhubaneswar is a nice place. Visit Puri, Bhagwan Ji ko bhi aata hai, Jubilee is a nice place.
No, we have a lot of students coming from Israel. This EAGA thing, almost
From where? Israel?
No, HM.
HR.
16 of the students is here.
Okay.
Okay, so now there will be a break for about half an hour. So we will meet again at 3:45 p.m. Tea, coffee, and cookies will be outside. 3:45. Yeah. We meet again at 3:45.
So, attendance is done or not yet? Attendance is done.
Excellent.
Then don't come to take. Don't go. So yeah, don't copy.
Hello.